Hello everyone. In this lesson, we will talk about low-frequency electronic circuit. Chapter 5, Negative Feedback in Amplifier. We are learning deep negative feedback today. So what is deep negative feedback? Loop gain or feedback depth. When it is much greater than 1, we call it a deep negative feedback condition. What is much greater than 1? Normally, 2 orders of magnitude larger than 1. For example, 120,000 of this chord is much greater than 1. When this condition is met, this negative feedback amplifier is what we call deep negative feedback condition satisfied, a basic amplifier that meets the deep negative feedback condition. There are some changes in the input and output resistors. Let's take a look. Then based on the depth feedback condition, source closed loop gain equals 1 plus source gain multiplied by feedback factor over source gain ratio. Since the 1 plus source gain multiplied by the feedback factor is much greater than 1, that means the latter one is much larger than 1. The denominator is approximately equal to the source gain multiplied by the feedback factor. So the molecular denominator takes away the source gain. The source closed loop gain is equal to 1/2 of the feedback factor. Then the closed loop gain is equal to 1 loop gain divided by 1 plus open loop gain multiplied by feedback factor. The same thing. If it satisfies the feedback criteria, closed loop gain AF is also approximately 1/2 of the feedback factor. When this condition is met, let's see how its input and output resistance change. When the deep negative feedback condition is satisfied, its input resistance, if it is inline feedback, input resistance equal to the base amplifier, input resistance multiplied by feedback depth. So, because the feedback depth is much greater than 1, multiply 1 more input resistance, we can think of it as approaching infinity. Then, the input resistance of the parallel feedback circuit equal to the input resistance of the basic amplifier, are a ratio of feedback depth. Because the feedback depth is much greater than 1, we think close the loop. Input resistance of feedback circuit approaches 0. Output is a voltage feedback. Its output resistance should be basic amplifier. Output resistance divided by feedback depth. Feedback depth tends to infinity. For this deep negative feedback condition, the output resistance of the voltage feedback circuit approaches 0. If the output is current feedback, we know current feedback. What is its output resistance? Equal to the output resistance of the basic amplifier multiplied by a feedback depth. So, because the feedback depth is much greater than 1, so negative feedback circuits satisfying deep feedback conditions, circuits in current feedback form, its output resistance approaches infinity. Let's take a look at those that meet deep feedback criteria. Amplifier circuits, its resistance changes so much. It's actually consistent with how we use this negative feedback circuit. For one purpose, for example, when series feedback is used on the input side, the extracted voltage signal is the signal. We want the larger the input resistance, the better. That's good. Deep negative feedback amplifier circuit. If feedback is in series, then its input resistance approach infinity becomes more ideal. That's the opposite. If the input inside is parallel feedback, what we want to extract is the current signal. The smaller the input resistance, the better. All current goes to the input port of the amplifier. So what about the amplifier circuit with this depth feedback, also approaching this ideal? The current of the input signal can be extracted very well, so it satisfies the deep negative feedback condition. Amplifier parallel feedback is also more idealized. That output side, if the output side is a voltage feedback, we want all this voltage signal. At output, it is not affected by load sides. That is, the smaller the output resistance, the better. Then those that satisfy the deep feedback criteria, these voltage feedback circuits, its output resistance approaches zero, so it's also very ideal. So what about current feedback? Its output resistance, we hope the bigger the better. In that case, all output current signals fall under load, not subject to changes in load resistance value. The output current has a significant change, so just this kind of current feedback, amplifying circuit with deep negative feedback. Its output current performance is better and more ideal, because its output resistance approaches infinity. All current falls on the load. No changes with load resistance value causes a significant change in the output current. That is, an amplifier that satisfies the negative depth feedback condition, its performance matrix are more ideal. Let's see if we've met in depth feedback. It also brings one benefit, performance of basic amplifier. Overall performance in negative feedback amplifier is no longer reflected, or it has a little impact. Look, because it satisfies the feedback criteria, negative feedback amplifier, closed-loop gain is approximately 1/2 of the feedback factor. So it depends on the feedback network. And with the performance of the basic amplifier, we can't see from this formula. That is, if the amplifier circuit meets the requirements, deep feedback conditions, then the performance of the basic amplifier in the feedback amplifier circuit. If there are some errors or deviations, what is the impact on the performance of the entire amplifier? And it gets smaller. If it satisfies the feedback criteria, let me give you an example. Such as a negative feedback amplifier, feedback factor Kf equals to 0.1. The gain of its basic amplifier equals to 1000. Let's figure it out. So what is T equal to? T equals to 100 and is much greater than 1. Should be deemed to satisfy the feedback criteria. What is its closed-loop gain equal to? Closed-loop gain equals 1 plus T of A, right? Just set T is 100. The 1000 of 101. So close to 109.909. When the gain A of the basic amplifier changes, for this, the overall performance of the negative feedback amplifier is not affected. For example, the basic amplifier performance changed from 10,000 to 10,000. Will there be any significant change in the performance of the closed-loop amplifier? It can't. Let's calculate. Closed-loop gain equal to 1 plus T plus A. It's 1,000 to put this in. 10,000 tens of a million. It is also approximate 9.989. We found that this satisfies the deep feedback criteria. Closed-loop gain of a negative feedback amplifier. This happens at the basic amplifier gain. When performance changes tenfold, there is no significant change in the closed-loop gain. It just changed from 9.909 to 9.98. This amplifier with steps feedback. Its performance is influenced by the performance of the basic amplifier, smaller, or after you have met the deep feedback criteria. Negative feedback amplifier has stable performance. Let's calculate the negative feedback amplification. Circuits meet depth range condition. Its performance indicators, for example, its closed-loop voltage gain, or what is its closed-loop current gain exactly. Let's calculate. So for such a calculation problem, we have that very clear set of analyzed steps. There are 4 steps. Everyone must remember it. First, we want to amplify this original negative feedback circuit, split on output side, taking into account the feedback network load effect. Output side of basic amplifier, that is, the basic amplifier shown here, and the feedback network, Actually, we still need to make further changes to it. Consider splitting it up. Basic amplifier for feedback network load effect. Calculate its feedback factor, basically based on the basic amplifier. Output side of basic amplifier for feedback network load effect. So long as we get this, we get a feedback factor. So we just want to get it. Taking into account the feedback network load effect, the output side of the basic amplifier is fine. So how do I get this quadratic feedback? Output side of the basic amplifier for network load effect. First, based on how this feedback network is connected at the input side. If this feedback network, basically the input side is in series feedback, then we will open the input AC. If this feedback network parallel feedback at the input of the basic amplifier, so we'll basically amplify this. Input short-circuited to AC. In that case, we've got 1. Feedback network has nothing to do with the input side. That's it. Getting a feedback network is all about output connection of basic amplifier, such a graph. This picture we can say yes, a crude output of basic amplifier for feedback network load effect, with this included in the feedback network load corresponding. What about the output of the basic amplifier? So we can calculate the feedback factor. So how to calculate the feedback factor? The feedback factor is calculated in this way. It's the output signal of the feedback network divided by the input signal of the feedback network. That is, the base amplifier's output signal, a feedback signal generated by a feedback network. Output signal comparable to the basic amplifier. This is the feedback factor. According to it, the depth feedback condition is satisfied. AXF equals 1/2 of the feedback factor, or AXFS equals 1/3 of the feedback factor. That is, the closed-loop source gain is equal to 1/2 of the feedback factor, or the closed-loop gain is equal to 1/2 of the feedback factor. We need to know exactly what its X is. That is, according to 1/3 of the feedback factor, the resulting closed-loop source gain is either what is closed-loop gain input and output signal, is closed-loop source voltage gain or closed-loop source current gain, or closed-loop source mutual conductance gain or closed-loop source mutual resistance gain. This is important. What exactly is this X? It is entirely determined by the type of the feedback network connection. If this feedback network is a voltage series feedback, then the output signal is voltage. The input signal is also a voltage, so deep negative feedback, 1/3 of the resulting feedback factor, should be equal to AVF. AXF, this X is V. Because of this type of connection feedback, the output signal is either a voltage input signal or voltage. It's the ratio of two voltage we call AVF. It's closed-loop voltage gain. So if it's a current series, that is, the input is a voltage signal, the output is a current signal. What exactly is this X? Output is current input voltage, so it should be a mutually conductive gain. So, depending on this connection type, we know it should be AGF equals 1/2 of KF. The same thing, according to its connection type, we know when deep negative feedback is satisfied. Feedback network connection type is voltage parallel. Output is voltage, input is current. It should be 1/3 of feedback factor. Closed-loop resistance gain is ARF. If the current is in parallel, output is in current inputs as well as current, so 1/2 of this feedback factor equals closed-loop current gain is AIF. So the third step is very important. Step 3, we have to figure it out. What is the ratio of output to input for closed-loop gain? This output and input is completely determined by the type of feedback network. For example, is a voltage series. Output is voltage input as well as voltage. Then 1/2 of the feedback factor is equal to closed-loop voltage gain. Its AVF is the first. Step 3 we need to figure it out. You get a feedback factor of 1. What is the corresponding AXF equal to? There's a fourth step because you asked for it in the calculation. A closed-loop gain. Often, it's not just the third step we did depending on the type of network. The type of the closed-loop gain determined. For example, the feedback type is a voltage series. Then 1/2 of the feedback factor should be AVF or closed-loop voltage gain. But what do you ask for is the closed-loop current gain. Then you have to get 1/3 of the feedback factor. Subtract to AVF, make it AIF. So there's a fourth step. That's the AXF we got in step 3, gain type required to convert to the title. There are 4 steps. All circuit analysis satisfying deep negative feedback conditions. Let's figure it out with an example. Okay, this is the end of this class. Thank you.